All right. So what you can do is you can go to this GitHub repo. If you click here, YN, and you can get the practical, download it. You probably did. If you did this previously, or if you're watching in retrospect, then you can just do it now. So this is a practical associated with Unit 4. It's not the fourth practical, the practical associated with Unit 4. And there's quite a lot of goals in this practical. So we're basically going to do a deep learning A to Z, but we'll skip many bits. And convolutional neural networks are next week. Stop me at any time, Matt, if you have a question. See, okay. All right, so with this, oh wait, so I can actually stop and are you actually present, Matt, or do you want me to wait? So since you're the sole live student, I can wait a second so we actually do this live with you.
I'm happy for you to read through this while I set up the lab notebook.
No worries. Okay. And hi, Aspara. So we went from 0 participants to 2. So,
great. Hello.
hi. Okay. So now we can compute the standard deviation before we of the students. No, before we only had 1. So I'll actually just start again, also for the recording purpose. Yeah. All right. So thanks, guys, for joining. The Julia folks. All right, so I'll just start again real quickly. So welcome to the Mathematical Engineering of Deep Learning, the 14th hour. This is a split practical dealing with Unit 4, General Neural Networks. I'm Yoni Nazarathy, and I'll be doing the Julia practical. In parallel, we have an R practical by Benoit Liquet and a Python practical by Sarat Moka. So you can open the practical link, and what we're doing here is dealing with the flux package. Any Julia package has the suffix .jl. Also, Julia files have the suffix .jl. That's a flux package, and that's a native Julia package for deep learning. And we'll try to do quite a lot. We'll see how much how far we get. So I'm going to run this first cell. Like the previous, and stop me at any time if needed. Like the previous practical we had for Unit 1, which just dealt with the data. Here we also deal with the MNIST data, but this time let's get it from the flux package. Previously we got it from ML datasets package. So here is like if I run this cell, so the train label associated with the first image is 5. That's this show. And if I just output the train images, then this is the image 5. So it's 28 by 28 data. All right. Now, what's happening in the other practicals in R and Python is scaling of the data set. However, the way things come in Julia, at least with FluxGL, you don't need to do this. So if I do the type of this first image, then what you see is that it's a norm uint8. Uint8 means it's an unsigned integer of 8 bits, just a byte, okay? So values from 0 to 255, but it already has kind of a normed type to it, meaning that it's represented as a number between 0 to 1, okay? So the integer is divided by 255. And then it's a two-dimensional array of uint8. And you don't have to go to all these details, but the thing is that Julia decorates the type of the image, and that's one of the things that allows it when we just say write the image here. It has a display function which will display it as an image. Okay, so it's not just an array; it's an array with a special type. But basically, it's an array of numbers. Okay, so I could have done something like, for example. Just so you see, I could have done float 32 mapping on this image. So this broadcast operator of the function float 32, which actually converts it to float 32. And here you just have a 28 by 28 matrix of 32-bit floats. I could have also done float 64. We typically don't need to worry about this unless we're really becoming deep learning professionals. But just so you know, in deep learning, people actually care about working with 64 bits, 32 bits, 16 bits, etc., because when things run at scale, often you don't want the full bits for the float. So working with 16 bits is actually quite common. Okay, just to keep that in mind. But that's beyond what we're doing. Okay, so the first thing we're going to do we're going to do classification. We're going to use a package. We're going to do several things. The first thing to do is to use the one hot batch function. So here's the help for one hot batch. So one hot batch basically takes it works by default already on a list of elements, and you tell it what labels you want to do things in. So you see train labels. Let's just see, here's train labels. Train labels has 60,000 because that's a training data size labels, labeled from 0 to 9, right? These are the digits 0 to 9. I'll just delete this. And if you apply one hot batch to it and you say the possible entries are 0 to 9, well, the length of this range is 10, and it's going to create this matrix of 10 by 60,000, where each column is a one hot batch vector for the image. Again, here Julia and Flux uses kind of the type system, and the memory is actually not allocated for it. This didn't kind of multiply the memory that we use by 10. It's not such a big deal with 10, but say if you're doing a classification to one of 1,000 types, you don't want to do one hot batch and suddenly allocate all this memory. So the system's kind of smart and, just writes it like this, but represents it still in a linear format as it obviously can.
Is it just using a sparse representation of that matrix?
Yeah, that's what it's doing. So the one hot matrix type, you could go to the code of one hot matrix types and then see that it's sparse, exactly as you said.
Yes.
Right. Okay. Now we get to kind of a whole bunch of code that organizes the data. I won't dwell on every little point here, but let's just see what this is about. So this is a hyperparameter choice for the batch size. So this is the mini batch size. Okay, the mini batch size, what does it affect? I mean, it affects, first of all, how fast it takes us to do a forward pass and a backward pass, right? Because each forward pass and backward pass is for a fixed mini batch. But it also affects the form of the, let me call it quasi-stochastic gradient descent. Mini batching is an approximate form of stochastic gradient descent. Right, so it actually turns out that if we would have done the batch size 60,000, so we've only had one mini batch, then there'd be no randomness in the gradient's descent, and the optimization can actually get stuck in local optima. So stochastic gradient descent has kind of almost by chance, no pun intended, this kind of extra benefit of giving us a bit of running away with a gradient that's not going to be exactly the precise gradient. But that's a hyperparameter one often tunes. Now, if you'd continue on and do deep learning on kind of, GPUs and things like that, where you actually really need to think about performance, and that's where real deep learning is kind of taking place, then the size of the batch size also needs to consider the architecture of the GPU. Okay, so you want to be able, ideally, to store everything in the fast memory of the GPU. But that's kind of beyond us. Okay, now validate fraction, what we're going to do is we'll keep 20% for validation. Okay, so we're going to take our test data, our train data, our 60,000 train images, and 80% will be for training, 20% for validation, right? The test we're going to keep on the side. We'll do this in a clean manner where we only touch the test afterwards. Okay, we'll treat the test as though that's how you do it professionally. So training, validation, test. Okay, so then this is a num train. This should be 60,000. And now we're creating these ranges. This is just a bit of kind of long code. This is kind of a range. These are the indices of the training data. Okay, and these are the indices of the testing data. So from here +1 on to 60,000. Now, what this function mini batch is going to do, we're going to give it X and Y data, and we'll give it a range. We'll give it a range. And what it's going to do is it's going to organize the data in the way we want. Now, the standard way to put in data into Flux is already kind of thinking image data. even though, you know, this image data, we could have just vectorized the image to 784 pixels. But soon, next week, when we go to something like C410 or in general bigger images, you want to think of like a tensor. So you've got your width, you've got your height, and you've got your depth, and you've got your batch size. Okay, so it's a 4 tensor. So every bit of data is a 4 tensor. I'll show you it in a second. So what this mini batch function does, it gets both the features and the labels and an associated index range, and it returns this type of object, which is a tuple of two things. It's a tuple of your 4 tensor, okay? The 4 tensor that has width, height, depth, which will be one in this case, and batch size. And the other one is like the chunk from this matrix, which is of the batch size. Okay, this is how Flux works on data. That's what it expects. It expects this kind of tuple of things. I'll show you in a second. Okay, so again, this is a whole bunch of call this kind of code that's kind of, you have to have it for organizing the data, and that's where often things take a bit of time to handle. You don't have to have this particular code, but some variant of this. Okay, now this partition is going to now take all of the training images and create kind of these ranges, each one of batch size 128. Okay, probably leaving if 60,000 is not exactly divisible, or the number is not exactly divisible by 128, 60,000 times 0.8 is not divisible by 128, it'll leave some spare. And finally, the training set is then this, for us, what we're going to do in the training set, it's going to be, this is a comprehension. It's an array of mini batches where each time BI here is for each one of the mini batch indices. Okay, so each one of these guys is like a range. Okay, and this is also just a one batch train set, which is just the train set all together, like in one batch. We just use this later. I'll show you why. Now, similarly with the validation, but with the validation, we don't want to break it into mini batches. So what we're going to do with validation is we're going to check the accuracy as we train to see that we don't overfit. Okay, so if we run this, let's just look at, for example, one batch train sets. So let's see what this thing looks like. So it's hard to see from this what it looks like. So what I can do is I can do type of this thing. Okay, yeah, this is Julia specific. So it's a tuple. Okay, a tuple is, you know, as you know maybe from other languages, or maybe you know in Julia already, you know, a tuple is an immutable array. It has two elements. Okay, so this is a tuple where the first element is an array of float 32 4. That means it's a 4 tensor. Okay, so this is actually your data. And your second element is your Y. Okay, so that's how this is the type of the one batch train set. So for example, if I would do one batch train set 1, that would give me this tensor of the data 28 by 28 by 1 by 60,000. If instead of one batch train set, I would have just gone to train set 1. So train set 1, let's look at the type of train set 1. It in its own right is such a tuple. So if I'd go to train set 1, because it has all these tuples in its own right. So if I'd go to train set 1, 1, then that is a mini batch. So there we go. We just see a mini batch. So it's 28 by 28 by 1 by 128. And again, if we would have had a color image, what would change here if we would have had a color image?
28 by 28 by 3 by 128.
Right. And if we would have gone for mini batches of 1,000, we would have had here 1,000, etc. Okay, so that is the first mini batch. That is the second mini batch. Oh, sorry, that is the second mini batch, etc. And what you just saw there is the first one hot encoded. You see, these are 128 one hot encoded vectors that are associated with this mini batch. Okay. All right, so roughly, I hope you kind of see how the data is organized. And again, when you do this yourself, you'd want to fiddle with it a bit more. But at the end of the day, you just make it work. Okay, so let's invoke some packages. This sets a system seed. Now, I must say that the training neural networks in general in a reproducible, you often set random seeds to make things reproducible for demonstration purposes, for debug purposes, for scientific purposes. There are other reasons to set the random seed of the pseudo-random generator. However, getting reproducible neural network training often requires one thing beyond, because often there's parallelism taking place, so it's hard to get fully reproducible training, just so you know this. Okay, so we're using beyond the basic things that come with Flux, the statistics package for mean, random for this random.seeds, plot for plotting, and cross entropy comes from Flux. You need to actually tell the system you're going to use it. One hot batch we used already. One cold is like the reverse of one hot batch. One cold takes this thing and returns the index on which you're turned on. Okay, that's it. All right. Now this, in the sense, in what you're seeing now, is the most important cell of this practical. This is our model. This is our model. Now, in Flux, what you do for a model is you use this chain function. Now, functions in Julia that have a capital for the first letter are often meant to signify constructors. So that it's both a function, but it creates a type. It creates an object, okay? And chain gets a variable number of functions as arguments. So what you're doing, it's very kind of verbose. You're chaining a function to a function to a function to a function to a function. Now this first function is just going to be a flatten. So it means that whatever tensor you put in, it's just going to flatten it into a vector. Okay, but we could have had a different first function. We could have had raise every feature by 2. We could have had other things. We didn't necessarily have to have the standard neural network elements you have. You know. Now, this function creates a dense layer that uses 784 that outputs 784 neurons, and that outputs 128 neurons, and works on 784 inputs. Now, this assumes this comment assumes 28 by 28. You know, we're designing this model for inputs of 28 by 28. Okay, that's the 784. What is this?
The activation function of the first hidden layer.
Exactly, that's activation function. Now, if we would have not used if we would not put that, the default parameter is the identity function. So then it's just going to be a linear layer. So it's not.
You've got that in the final layer, right?
Yeah. So we often put that in the final layer as we did here, because we're going to do a softmax, right? So this came with a default identity, and you could have written sigmoid instead, or tanh, or something else. Okay, for the activation function. Okay, so that's a model.
I had a question about the model. I think I know the answer to this question, but just get your thoughts on it as well. We use softmax at the end because we're doing classification, but you know, it's not like it's an activation function. Can you sort of explain why softmax is not in the dense constructor like ReLU is?
Yeah, for sure. So softmax is not an activation function, because an activation function operates element-wise on a neuron. An activation function is a scalar function where you take the output, after you've done the linear operation or the affine operation, W input plus B, apply activation element-wise. Softmax has in its denominator the whole spiel. It has all 10 neurons. So softmax actually operates on this 10 vector. Okay, I'll actually show you in a second. So it's a good question, but yeah, so we couldn't have specified softmax here. We cannot do that because then this function would just be applied element-wise on each of the 10 neurons. But softmax needs to know the totality of them because in the denominator, there's the sum of the exponential of them. Okay, so softmax is a function from Rn to Rn. Well, from, in this case, from R10 to R10. It's not a function from R to R.
Yeah, thanks.
Okay. Okay. So now, just to debug this, let's create a test image. So the way of creating a test image, this is a bit annoying, but this is how we initialize an empty array, an array with undef of 28 by 28 by 1 by 1. So this is like a mini batch of size 1. And then rand exclamation mark is going to put uniform 0, 1 values in it. So this is like a random test image. Okay. So it's just static noise, random test image. But it's good after you created a model to apply to the random test image, because look, if I do now model on the test image, I get this. This is not exactly my classifier. This is the output of the softmax. So in this case, what digit did our model predict? What digit did it predict? Not 0, not 1, not 2. It predicted the digit 3. Okay. Of course, the model was with uninitialized parameters, and we put junk in, so everything is junk, and so we get something that's roughly uniformly distributed. Okay. Now let's just look a bit more into our model. The length of the model is 5, and what we can do, this is kind of nice. If we do model 1, we just take the first, so a model is an array, actually. We take model 1, it's just the flatten. So we can apply that to the test image. So see, test image was this 4 tensor, right? 28 by 28 by 1, 1. If we apply the first element of the model onto test image, so this is apply first layer onto test image, then, you know, we get this flattened thing. And now we can apply first 2 layers. And then we get our 128 neurons. Okay, and we can apply the first 3 layers. Now, when I say here layers, don't confuse that, you know, layers like the flatten is not a layer in the mathematical sense, but it's a layer in a function change in the model sense. So then we get the 64 by 64, and we can continue this thing, you know, apply the 4th layer. Then we get this, and this is now related to your question. This is the output of this linear layer prior to the softmax, and then this 5th thing is just going to apply softmax. This is a full model, it's going to apply softmax onto this. So it took these values, applied softmax, but it summed the exponential of each individual entry, put that in the denominator, put the exponential in the numerator, and gave us this probability. And if we sum the answer, of course, it's going to be 1. That's just a property of the softmax.
So we have these.
This F.
Sorry.
Yeah.
So we have these sort of layers, which are the ones like we've studied in class with the dense layers. But then we also have these kind of like, would you call them normalization or just like processing layers, where they would operate potentially on the whole data set. That's not what I mean. Potentially on all of the outputs, like the normalization thing. That's not something, it's not element wise, like you said.
Right. I mean, we don't have normalization just yet, but we have these software layers, right? I mean, we could have thrown in another flatten here, okay? Or if we would have wanted to, there's no need to, but we could have, right? Or we could have thrown more functions in there that operate. What this function needs to do is work on this input argument and be able to put its output argument to this next thing.
Yeah, and probably it needs to be differentiable or something for the training.
Yes, although Julia would just use, Flux would use automatic differentiation, so almost anything is differentiable.
Cool.
So it's, you know, so then you can use functions that are you know, arbitrary functions that have a for loop in there, etc., and it will do its best to differentiate it. Sometimes it won't be so fast, but it'll do that. Okay, and this F0 just means it's a float 32. These are how literals of float 32 are printed. That's this F0. Okay, so a lot of the things I'm saying are obviously very Julia specific. That's the nature of this practical. So this is a definition of a one-line function. This is just like defining a function, but it's defining the function accuracy. Mean came from the statistics package. What does accuracy do? It just does one called on the model on X. So apply one called on everything and see if it's equal to the one called of Y. Okay, and take the mean of that. So the percentage of one called of the proportion of one called X, one called Y. You could have done this in different ways. And this is the, so we give the model as a parameter here to the accuracy function. And this is the loss function. We're going to use cross entropy loss, okay, as is common in classification. And we'll give it the model, it'll apply the model on X, and it'll do its cross entropy with respect to Y. So again, these functions assume that the Y is in a one hot vector case, and that everything's in the right setting. Okay, now we finally get here, if you want to do, by the way, in eta, you do eta tab, okay, if you want to write like eta, like that. Okay, so that's going to be a learning rate. Okay, learning rate. And we're going to write our function, which is called train model. Okay, now, just so you know, in Flux, Flux is kind of, it's not used at the moment in like PyTorch or Keras or TensorFlow. Well, Keras uses TensorFlow typically, you know, industrially, but it can be, and some people use it. It's just that it's kind of making headway. But one of the nice things in Flux is that everything is written in Julia, and it effectively runs as fast. Okay, so just to see this, let's use this. Here's this Atom constructor. That's the Atom optimizer. Okay, so let's go to Flux.jl. So that's the GitHub of Flux.jl, the library. Okay, now you can open the docs, and that's fine. You can do that later and read some of the documentation of Flux. But what I actually want to show you, I actually want to go to the source code. Because when you use a different deep learning framework, like our friends are doing now in the parallel classes in R and Python, they cannot see the code in R and Python. It's not written in R and Python. It's written typically in C++. Okay, so let's go, for example, to the optimize folder. This is actually the Flux source code. Of course, it's open source. I mean, PyTorch and Keras, etc., are also open source, but you can't reach the sources easily if you're a Python developer or an R developer. So I just want us to look at the optim. I don't know why this is working so slow. Oh, I see. I think I've changed off. Let me. Sorry, I have a slight technical issue. Let me change to the phone hotspot again. Sorry, I've had a bit of a technical issue. Can you hear me now? Okay, I just changed to the phone hotspot. So we're here in the Flux source optimize, and let's open this optimizers.jl. Of course, you don't need to read this fully, okay? But I just want to show you actually the code for the Atom optimizer. So this is the apply function, which actually does an Atom optimization step. This is it. That's here, right there. Now, you know, some of it might not be clear from immediately, but first of all, a few things. You learned about Atom just a few days ago with Sarat, okay? And Atom basically does a momentum step and also does an RMS prop step. And that's just embodied in these three equations. So this is operational fast code. This is actually the square root function, okay? And this is the, you know, so you can call variables like that as delta and stuff like that. Okay, so these are parameters. But what I want to show you is that the code is quite accessible. Of course, some things such as types, etc., you need to read a bit more, and you might maybe want to understand what this macro does. This macro says, please do all the evaluations on the right-hand side as element-wise. Okay, that's what it tells, because it's going to do all this block-wise, element-wise things. But I just wanted to show you that Flux code is accessible and is in Julia and is typically very light. Okay. So back to our usage of Flux. So these two arrays here, what we're going to do is we're just going to keep empty arrays of the valid training losses as we go, the validation losses as we go, the training accuracies would proceed, and the validation accuracies would proceed, empty arrays. And let's define this function with, after this function, this is like, you can call it a callback function, but we won't use it as a callback. Sometimes to a neural network framework, you can do it with Flux as well. You tell it, please, after every mini batch or after every epoch, do a callback. You give it a function and it calls back the function. In this case, we'll just do it manually. And this is just going to compute it's going to add to these arrays. It's going to push into the arrays or append to these arrays the loss on the training set, the loss on the validation set, the accuracy on the training set, the accuracy on the validation set. These three dots in Julia, the ellipsis operator, that just takes the two elements or the multiple elements of, in this case, it's a two elements because it's a tuple, and it puts them as two arguments for the function, x and y, right? Loss wanted x and y. And this is a tuple of two things. Okay, it's equivalent to putting the first and the second in there. Now, this is just a call to the model on the first. This line does nothing, line 13. It applies the model to the first mini batch. And the reason we do it is when the compiles it, it kind of helps it, well, it's for performance. So it's kind of a warm-up step. It's kind of a, hey, get ready, run it once before you kick into the loop. Okay, it's not critical, but that's speed up when you run once. Okay, now we're going to loop over all the epochs. Okay, for epoch and the number of epochs, and in Julia, after a semicolon, these are called arguments that their order doesn't matter. They're named arguments. Okay, they have defaults and they're named arguments. You could have also had in a function default arguments before, but then the order matters. So, you know, that's so often you just, yeah, that's epochs, that's optimizer, and verbose true. Also, the verbose, we wanted to print stuff. Now, this is here the key line where we actually do something with Flux. Okay, this is, okay, here is the beef. I mean, I'm actually vegetarian, but the beef is still there. Okay, so this is flux.train exclamation mark. This line's going to do a whole lot. What does it do? It expects a loss function. Now, we give it the loss function. This is here an anonymous function. It means whenever it says, hey, function train, whenever you get an x and a y, you plug it in there and we'll tell you what the loss is. Okay. It expects the parameters of the model. So params takes this model object that exists, extracts all the parameters of it, and gives the reference of that to Flux. It expects the training set. Okay. Yeah, which is the set, in this case, train set was our collection of mini batches, okay? And it expect the optimizer. The Atom optimizer has state, right? It's not like simple gradient descent or simple RMS prop that's state free. It has state because it keeps learning. The momentum is a state and it also keeps the second order condition. So it's also going to modify the optimizer. So that's the optimizer object. Now, there are different ways to actually invoke training in Flux. This is one of them. Okay, so this is training for one epoch. We could have actually gone to the mini batch level. Okay, and we could have also done it in kind of a more external level. But here I chose this way to show it. Then we're calling our own function update after epoch, this function here. Okay, which is just going to kind of record everything. And then here we're going to say if verbose. This is called short circuiting in Julia. Okay, it's just if verbose is true, then do this. Okay, so the lazy AND operator is only going to evaluate this statement if this statement is true. It's kind of a Julia idiom for writing things. Print len, the epoch, that's how you print the epoch, validation accuracy, round, etc. Okay, and then return a for tuple of all these things so we can plot it. Okay, so let's run this thing. So return this and keep it in traces and also do the final validation. And now the validation accuracy here is quite high already because MNIST is not such a hard data set. Okay, so we get that up to, it's going to continue for this number of epochs, the default, which is 25, which is 99%. Okay, so we've created this other function here, plot model. This function takes the traces, takes something like this. Okay, it assumes it's a for tuple. Okay, so it extracts this from the for tuple, traces 1, traces 2, traces 3, traces 4, and then it's going to plot the trace of the model. So what we see is over the 25 epochs, I won't speak too much about the plotting, just ask me if you have questions. So over the 25 epochs, we see that the validation loss and training loss pretty much behave the same. We could have probably stopped here. When we see a point like this that it's not so clear here, but in certain cases you'll be training and you'll be seeing that the validation accuracy reaches a local optimum or an optimum and then decreases. And that's an indication of overfitting. We don't fully see this here. Okay. Yeah, I mean, there is maybe a potential overfit after 10 epochs, but that's not so clear. Okay, any questions so far?
About the flux, excuse me.
Yeah.
About the flux train function, could we recap what that would involve? If my understanding is right, it's going to do a backpropagation based update on the parameters of the model, using the optimizer, like to decide what the new parameters will be. And oh, okay, so it's a full epoch, right? So it's going to go through each of the pairs in the train set. It's going to call the model or the loss function, the anonymous loss function that we've given, which involves calling the model to get the output. It's going to maybe somewhere in the model or in this influx, it's going to do the automatic differentiation. So it figures out what the derivatives are, and then it will use the optimizer to decide the size and the direction of the update. And we'll apply those to the parameters, which we've given it here using this reference.
Perfectly summarized, yeah.
Okay, cool.
Well done. Yeah, the automatic differentiation, we're doing here backward mode automatic differentiation. I mean, you learn about this from Benoit, right? So that's basically doing a forward pass, keeping the values and doing back propagation. Okay. I think in certain sub-elements, if needed to kind of do a local, so say I would have put, but this is what I'm saying, I believe with some certainty, but not 100% certainty. So if we would have put here some other funky function, okay, then it might do forward mode automatic differentiation of this function and continue backwards, like inside, but I'm not sure. Flux uses an automatic differentiation framework called zygote.jl, and in the Julia community takes a lot of pride in this automatic differentiation because it's actually it's kind of code to code automatic differentiation. Because of the nature of Julia, some quite advanced things can happen there.
That's very cool.
Yeah, cool, great. Yeah, but you summarized train perfectly. That's pretty much what it does. So a similar function to kind of be aware of. So that was train exclamation mark. Why exclamation mark?
Well, it's mutating something. I'm not sure if that's a mandatory or if it's just a convention that you should put the exclamation mark.
It's not mandatory, but it's a convention. But exactly like you said. And you could have also looked at flux.update. So update does less than train. Update just does a single gradient descent step. Okay, so train wraps update. Okay, I think in next week's tutorial, we'll just use update directly. Okay, so to update, you actually give a gradient. So you could have kind of separated these things. Okay, and then there's like one layer above, which I think we have at the end of this tutorial. I don't think we'll get there, but you could look at it. There's a macro epochs. So epochs just kind of is a macro that just does all the training without requiring you to do this loop. Okay, so there's kind of three main modes of operation. One is, I went for the middle one to kind of ride the loop of epochs. You could have done a one that's kind of, hey, run outside of everything. And you could have done an update, which kind of goes inside, and you would have had a step, please compute the gradient. Then you would pass the gradient into update, and you do a loop on the mini batch yourself. This we'll do next week. So Flux allows us to kind of have a hybrid between a kind of a closed package and something that's a bit more open. Okay, so this I'll skip simply because it's simple. So here we're looking at a test image, and we're just going to evaluate the accuracy. I'll just get to this point where this is our, and I'll skip because I want to move forward so we see just a few other things. This is our own predictor function based on a trained model. Okay, and the model gives us a probability vector. What this predictor function is going to do, you give it an image, it's going to reshape the image into the proper form. It's going to apply the model to that. It's then going to apply one cold to that. And then it's going to do -1 simply because one cold will give you indices 1 to 10, and we want digits 0 to 9. Okay, that's kind of, if you go over this later, you'll see the steps of creating the predictor. So like the predictor of the example image, which we have above, this is an example image. When we apply predictor to it, we get a 7. That's good. It is a 7. Here is predictor applied to all of the images, all of the test images. Okay, so we've applied. This is actually what we would then package this function and, you know, deploy to the app or whatever. The test accuracy is the sum of the predictions, which we just did. This is a list of Booleans, okay, of which almost 97% are 1, okay? And the sum of these divided by its length is the test accuracy. And here we just do by hand the confusion matrix. So for the confusion matrix, we just want to run I 0 to 9, like what is a digit? This is digit 0 up to digit 9. That's this I 0 to 9. And J 0 to 9. We're doing it, this is a 2-dimensional comprehension. And each time we're going to count what's the predictor of the image of all of the images. Count how many times for an image that was J, we got an I. That's how we get the confusion matrix. And if we sum the diagonals of the confusion matrix, here we need the linear algebra package to use diag. I'm just pushing a bit because we have a bit more coming in the tutorial. So it's a bit more interesting things. Divide that by the length, then you get the same prediction accuracy. Okay, so the diagonal divided by the total. Okay. Okay, so now comes the second part, where we're going to actually create a variety of models. Okay, and we're going to do some model selection. For this specific data, that's not actually the best data for this model selection because it's not challenging enough, but at least we can see how to do it. So this is one way to do it. I'm not speaking about a whole bunch of Julia things. So what we're going to do is we're going to look at 9 models of sizes small, medium, and large. In Julia, this type of thing is called a symbol. Okay, so the type of person is just a symbol. Okay, so it's just like using a string, but it's actually like a hard-coded symbol. And this is this. So we're going to create a dictionary. I assume you know what a dictionary is. A dictionary gives you a key. From a key gives you value. So in a dictionary, we'll have as keys a tuple of a symbol, small and medium or large, and the layers 1, 2, 3. And these are actually the entries. And it's going to give us an array of the architecture. Okay, so this is kind of, we're going to create a whole bunch of architectures through this function make model. At least you have one example of how to do this. Okay, so take, for example, this entry. This says the dictionary models add the tuple medium 3. So depth of 3, medium number of neurons. We'll have 64 neurons in the first layer, 32 in the second, 16 in the third. Okay. So here's now a function make model to which we give the size, small, medium, or large, and the number of layers. Okay, so what we're going to do is we're going to, and again, this is just programming really, but in this programming you see a bit how to kind of deal with Flux, how to create things, how to create a model programmatically, for example. So functions is going to be an array. It's going to be empty. The first thing we're going to push into functions is flatten, just like before, right? We had in the model flatten above. And now we're just going to pull out of the dictionary. This is the global dictionary models. Okay, so let me actually just go models. This is the dictionary models for each key. Like small one, we get the value, the architecture. You know, this is like the different models. Okay, so that's going to be the architecture. And when you run, you have to know how many neurons you had previously and what you're doing next. So previous neurons is for 784. You're going to loop on the number of layers which we have. Okay, layers is the number of layers we want. The neurons is going to be the first element of the architecture, the elf, L, this is L, okay, the elf element of the architecture. And then you're going to make a dense layer between the previous neurons and the new neurons. And you're going to push it. So you're just going to pop these things in, and the previous neurons is going to be the current neurons. And in the end, let's not forget this layer. What's the activation function in this layer that I've just highlighted? That's the last one. What's the activation function?
Identity function.
Identity, perfect. And then we're going to push a softmax, and then we're going to, there's an implicit return here. Okay, I can write the return, but the last thing in a Julia function is a return value. Or you can put undef if you don't want to return, or I think nothing if you don't want to return. But anyway, functions dot dot dot, it's going to use all these functions and push them in there. So then if we do make model medium 3, we've got a model medium 3. So let's use this. Model equals make model medium 2 in this case, traces train model on the model we've created. Let's just run for 5 epochs. Let it run. And there we go. I was supposed to have some, sorry, I don't know why this is here. Supposed to have a task there, but it was deleted somehow. I'm sorry. But the point is the task was now do this yourself on different models. So run, for example, on a model large 3 with 10 epochs. Okay. And you're going to get, so it's a larger model. It takes a bit more time. You're going to see how it behaves. Or you could have done something like opt equals RMS prop 0.01. Okay, so let's stop this. I'm just showing you now would use a different optimizer. This is another optimizer in Flux. So you can read in the Flux documentation about all the optimizers. Many of the optimizers Sarat spoke about, at least in the context of simple gradient descent first order methods, are in Flux. Okay, so there we go. The next thing to speak about is batch normalization. However, batch normalization didn't fit into the lectures that Benoit just finished yesterday. So I'll probably also speak about batch normalization as part of the convolutional neural networks. Okay, so here I'll just show how to use that. So basically, batch normalization is a trained form of normalization. You would have probably read about it in the notes as well. Okay. So a batch norm, so here's question mark batch norm from Flux. It's actually a let's call it again a software layer. It's not a layer in the neural network sense, but it's a layer that, in this case, it actually has parameters, right? Batch normalization, if you've read already about batch normalization, you actually train how to standardize the data, okay? So that's kind of a learned thing. So it's here, this is how we do it in Flux. We add a batch normalization layer. So here we have 128 neurons. This is a model, okay? We add a batch norm layer. Here we have 64 neurons. We add a batch norm layer. So this batch norm layer will actually have trained parameters, which will be the subtraction, kind of subtracting the mean and dividing by the standard deviation. But it's not exactly the mean and standard deviation. It's going to optimize those two parameters. We'll speak about it more in the Monday lecture. Okay. Here to see how it works, well, you just write that in, and then this thing works. So there's another batch normalization layer in there. Okay. I'll move on to the next thing, dropout. Okay, so you spent a bit of time in yesterday's lecture dealing with dropout. And dropout is, in a sense, a form of regularization. It's a crude form of regularization for deep neural networks. I mean, some people call regularization just the addition of a regularization term, an L1 regularization or an L2 regularization. You can do that to add a shrinkage component. Dropout does it in a completely different way by actually, during the training, zeroing out certain neurons. So not training all of the model parameters simultaneously. Okay. Now, for this, what I've put is this code. Now, the code is taken from here. If you click this on this, the code is taken, this GitHub repo, of which I'm a co-contributor, is for my Statistics with Julia book. So this is like a kind of, the book has standalone examples that work, okay? So it's not like these kind of Jupyter notebooks that have another thing and another thing and another thing and another thing. This is like, that's why it requires a few lines, you know, but it's never too much. So in these 52 lines, let me just overview what's happening here, okay? So what we're doing is we're looking at dropout, for different dropout probabilities, and we're doing a hyperparameter tuning for selecting the best dropout probability. I'll get to the details in a second. This would take a few minutes to run, so the output would look like this. The dropout probability can be 0, no dropout, 0.25, half, which is typically the common thing you would do, like, you know, 50-50 if you drop out or not, or full dropout, or almost full, 0.75. And each time, I think we're training 10 times, and we're looking at the validation accuracy in their box plots of the validation accuracy. So this is a crude demonstration form of seeing that the best dropout probability is maybe just the default dropout of a half, or maybe you can go to 0.25. Okay, there's quite a lot of discrepancy in these box plots that we get here. Okay, again, this takes a few minutes to run. Let's look at the model. Okay, let's look at the model and see how dropout is used. The one important object from FluxJL is dropout. Okay, now, first of all, this model has two layers at first that we, unless you've seen deep learning elsewhere, you still don't understand. They're convolutional layers. This is next week's lecture, okay, or the following lecture on this YouTube series, okay. Convolutional layers, we'll speak about them, okay. So they're convolutional layers, okay. They're not dense layers, not fully connected layers. They're convolutional layers, okay. And then there's flattening, and then, as is often common in convolutional neural networks, the common architecture is to have convolutional, convolutional, convolutional for a while, and then some dense layers that allow everything to connect to everything. So this model purposefully has too many dense layers, okay? Where the dropout is useful on, that's kind of a, you could have just written it like this, right? It's the, after each dense layer, we have a dropout. And Flux knows how to connect this dropout to these parameters, okay? These dropout probabilities. Now, this function eval accuracy is actually does quite a lot. You give it the dropout probability, it creates this model. It then does training, not with a for loop like we had before. This is training. You know, so again, here is the TOEFL. or beef. Okay, this is where it is. Okay, so it runs epochs for number of epochs, and epochs is here some global variable, 30. Okay, and it runs for 30 epochs, and each time it does flux.train as it did before, and it's just keeping everything in a results table and then doing this query. So this would have been like a complex homework assignment, not too complex, but right, that's kind of the type of thing here condensed into a few lines of code. And the idea is this is how we have the invoke dropout. And that concludes pretty much everything we were going to. Oh no, there was one more thing on overfitting, but we won't deal with this now. So, are there any questions?
Well, actually, there was one plot that you have in your notebook right now where I didn't catch which model you were training, but it kind of went up and then down again with both the train and the validation accuracy. That one. Could you speak to what might be happening there? I've heard of a phenomenon called double descent, and I don't know if it's that or if it's just sort of an artifact.
I'm actually okay. Good question. So when we see discrepancy between the validation accuracy and the training accuracy, for example, training accuracy goes to 1 and validation accuracy decreases, then we go, yeah, we found overfitting, and we stop. That's not the case here. These two guys are acting together.
Yeah, that's a good point.
So there might be a situation here where let's try and just run it again and just run this with the Atom optimizer, for example. Okay, it might be that the RMS prop optimizer with this learning grade is too aggressive. So this is where this is a bit of an art form, right? So and we could see what's happening. Too aggressive for model large 3. So model large 3 has 256 neurons in the first hidden layer, 128 and 64 neurons. So it's quite a bit of parameters, right? So the weight matrices are quite big. And let's see. Yeah, and then so it was a property of using a primitive optimizer. So RMS prop did not have momentum, or at least so we believe. Let's see if it's reproducible. Again, because we didn't reset the seed, and deep learning training is not so easily reproducible. Just so we know. But let's see if this thing persists again. Now, of course, I'm not running on a GPU. Not of course, but I'm not. This is a rather strong MacBook Pro, like a new one, but no GPU. You'd put this on GPU, things would run much faster. You need to do a few more things on the code with GPU. There's more on that on the FluxJL docs, but it's another line or two. Yeah, so this seemed like an optimization artifact. Okay, and then we can investigate it more. You might do something like this. Cut the learning rate by a factor of 5, maybe put 20 epochs, etc., etc. And this is where deep learning architecture is really important. We're working here with toy data sets, and we need to keep in mind that the big advances that have happened have been on massive data sets. I mean, we cannot do ImageNet in a quick demonstration in this course, unless I had access to a really fast GPU cluster. Okay, and then you probably won't have it. So when a lot of the things in deep learning just require the advancements are such that we as researchers can actually go through such playing iterations, scientific playing iterations in an effective manner. Right? Like here, this seemed effective. It seems like we reduce the learning rate. Seems like this thing is working. All right.
Yeah, thanks.
Okay. Any more further last things? Good, you caught that. All right, then. Have a good weekend. I guess you have a quiz if you're doing this for credit. Even if you're doing it not for credit and you want to suffer a bit on the quiz tomorrow, it's not going to be too hard. Enjoy it. And otherwise, see you Monday.
Thanks. Have a nice weekend.
You too.
Thank you very much.
Thanks. Bye-bye.